All right. So the next part about a sine wave. So the big idea in this topic is learning about what we call periodic functions. Okay, we've discussed this a little bit. How periodic functions are functions that they don't increase and decrease without bound, right? A lot of these end up looking like waves because they after a certain period of time, the pattern in the function repeats itself. Okay. And that period of time over which the function repeats itself, that's the period. So one informal definition here is the interval of the domain over which a function passes through all of its possible range. Okay. Now I've added my own little addendum to this where it says IE. That means the quote unquote time it takes for the wave to get back to where it started. So when you talk about the period of a sine wave, and again, here is our basic sine wave starting at the point 0, 0, going to its first critical point here, then back to an intercept point, then down to its minimum, and then back where it started. Okay, and I actually pulled up I have one here for you. You can see the whole wave is spelled out here. This is a basic sine wave. I put my sliders where I want them to be. So A is 1, B is 1, C is 1. So even though there's all this mumbo jumbo going on up here, it's really just sine of X. And in fact, let's make this 0. Okay, there we go. 0, right? So would be the graph of sine of X. And we can see. So when you look at starting at the origin, going up, then down, then to here, that pattern just repeats over and over and over again. We've talked about how the period of a sine wave, okay, is always 2 pi to begin with. That is the period of sine. But we can mess with that, okay? And when we were talking about transformations, we talked about how you can stretch or shrink a graph horizontally, right? You can compress it. We talked about shrinking or compressing, squeezing from the sides, right? If we took this sine wave and we squeezed it from the sides, it wouldn't look so stretched out. It would, right, wave back and forth a little bit faster, if you will. Okay, so that's one way to horizontally compress or horizontally stretch that graph out, right? So we can mess with this is the point. As a formula, okay, the period of a graph, so this is the basic period of the wave, right? It's always supposed to be 2 pi, but we can mess with that with a variable that we're going to put in here now. We're going to say b, okay? Now, I'm using lowercase b here. Suppose I should have done that in the Desmos window as well. This is the quote unquote formula for finding the period of a graph when you are given its function notation, okay? Because we've already seen well, if you haven't seen my video on amplitude, go look at amplitude, okay? And as we're adding this together, as we're adding more variables to this, the location of b is the coefficient of x. Okay, so think about this for a second. When we were doing transformations, again, we talked about inside and outside transformations. Inside transformations were what occurred inside the parentheses of the function, and it was always opposites day, right? So think about if b was a really big number, right? So let's look at a function, and we can throw this up in Desmos here in a second. Let's have the amplitude be 2, just because we're being difficult, and let's have b be 4. When I multiply x by 4 inside the parentheses, right, that's a horizontal transformation, and it's always opposites day. So when we're multiplying, we're stretching and shrinking. If it's a big number and it's inside, it's shrinking or compressing the graph. Okay, so if b in this case is 4, the period of the wave would be 2 pi over 4, which is pi over 2. Now what that means, and we'll see this again, we'll go to Desmos here in a second, but what that means is that doesn't mean we stop graphing at pi over 2. What that means is this wave, which starts, goes up, down, and then ends like that, that's all going to happen over an interval of pi over 2. So it's going to vertically compress, and we set a amplitude of 2, right? So I kind of have to, you get the idea, right? So the wave is going to be, it's going to be compressed in like this. The period is much shorter when we use a big number in here. So let's go to Desmos and see what that looks like. So I have a capital B here, lowercase capital, doesn't matter. Okay, I think MathXL uses capitals. But if I increase the value of B, look at what happens to the wave. Okay, like a slinky, right? It's getting compressed. If I decrease the value of B, I'm not going to make it negative, but I'm going to make it less than 1, right? Stretches it out. Think about opposites day. So the period of this graph right here, if B is 0.2, okay? If B is 0.2, that's 1/5, right? Stay with me now, okay? If B is 0.2 and this is 1/5, then we'd be talking about a period of 2 pi divided by 1/5, which would be 10 pi. That means to go from its intercept to its max, to its intercept to its min, and back to its intercept, it would take 10 pi units for that to happen. So let's come back and look at this, and let's zoom out and see. Here's the intercept. Here's the maximum point, okay? Zoom out. When does it come back to the intercept? At 10, all right? So it's not the number of waves that we see. That's frequency. That's a totally different ballgame. The period is saying, how long does it take for it to pass through its 5 critical points? Okay. If B is a really small number, then it's going to be stretched out. It's going to take a long time. The period has lengthened. If B is a really big number, that's going to take the whole thing and compress it. Okay. So just a few notes on period before we continue. Hopefully you're starting to see some of the connections between the transformations we did earlier in this semester and what we're doing now. Why do you think we spend so much time doing it? Right? Okay. Where is B? B is inside, and its opposites day on the inside. All right.